All right, welcome. In this explainer, we're going to build up the layers of safety for an electrical circuit step by step. We'll be using the Australian and New Zealand standard AS/NZS 3000 as our map, really digging into not just what to do, but more importantly, why we're doing it. So here's our game plan. We'll kick things off with the absolute basics. Then we'll get into protecting the equipment itself. From there, we'll talk about keeping the power on, tackle the really dangerous stuff like arcing faults, and wrap it all up with the most important layer of all, keeping people safe. Okay, first things first. Before we can even think about protecting a circuit, we've got to be super clear on what we're actually protecting it from. You know, every installation out there is facing two major threats from overcurrents. Now you hear these two terms, overload and short circuit, thrown around a lot, sometimes like they're the same thing. But in our world, in the world of circuit protection, they are completely different beasts, and each one needs its own specific strategy.
So the key difference here is all about time and cause. An overload is like trying to make your car tow something way too heavy for too long. The engine slowly overheats. That's what happens to your cables. They get dangerously hot over time, and the insulation can just melt away. A short circuit, on the other hand, that's an instant, violent failure. It's like a lightning strike inside the wire. The current just skyrockets to thousands of amps in a split second, releasing this massive amount of energy that can literally vaporize metal and blow equipment apart.
Now, this slide looks a bit technical, but it boils down the whole principle of overload protection into two really elegant rules. Let's break them down. The first one basically sets the pecking order. It says your device's reading has to be bigger than the normal load, but smaller than what the cable can handle. Simple enough, right? But the second condition, that's the real safety check. It makes sure that the current that's guaranteed to trip your breaker is still low enough that it won't cook the cable's insulation over the long haul. It's all about this perfect dance between the cable and the device that's protecting it. So we figured out the what and the why of protection. Now, let's talk about the where. Because where you physically put these protective devices is every bit as critical as picking the right one. This diagram here shows the golden rule. You can see the protection is right at the start of every single circuit. And it doesn't matter if it's a huge submain or a tiny lighting circuit, the rule is simple. Put protection at the origin. And also, you need it at any point where you switch to a smaller cable that can't carry as much current. It's just common sense, really.
But hey, the standards are written for the real world. And sometimes putting a breaker right at the origin just isn't practical. So there's an exception. This clause lets you move the device up to 3 meters down the line. But, and this is a big but, that little section of unprotected cable has to be rock solid, mechanically protected, and installed so the risk of a short circuit or fire is basically zero.
Now, this might seem totally backwards at first, but it highlights a really deep safety idea. You have to weigh the risks. Think about a giant electromagnet on a crane lifting a ton of steel over people's heads. What's the bigger danger? The cable overheating or that magnet suddenly shutting off and dropping its load? Yeah, the standard is crystal clear here. In certain cases, where losing power is actually more dangerous than the overcurrent itself, you must leave out the overload protection. Okay, so our cables are protected. Awesome. But what happens when a tiny fault happens on one little circuit? Do we really want the lights to go out in the entire building? Of course not. And that's where we have to design for reliability, using a concept called discrimination. The goal here is basically surgical precision. Just look at the diagram. If a fault happens downstream, we only want the device right next to it, PD2, to trip. We need the upstream device, PD1, to stay on, keeping the power flowing to all the other healthy circuits. That is the whole point of discrimination. You isolate the problem to the smallest possible area and cause the least amount of disruption. So how do we actually make that happen? Well, the main tool in our toolbox is this, the time current curve. Think of this graph as the device's unique fingerprint. It tells you exactly how long it'll take to trip at any given current. To get discrimination, you lay the curves for your upstream and downstream devices on top of each other. You have to make sure there's always a clear gap, a white space, between them, so you know for sure the downstream device will always be faster on the draw. And get this, the rules are different depending on what you're using. On the left, for common circuit breakers, there's a pretty simple rule of thumb. Just make sure the upstream breaker is at least 1.5 times bigger than the downstream one. But look at the right, for fuses, it's a bit more nuanced. The upstream fuse needs to be 1.6 times bigger for overloads, but a full 2 times bigger to handle a short circuit. It's a perfect example of how the specific gear you choose really impacts the whole design.
All right, now we need to focus on one of the scariest, most destructive things that can happen in an electrical system, an arcing fault inside a big switchboard. We're not talking about a little spark here. This is a plasma explosion. It's an event with so much energy it can vaporize copper busbars in the blink of an eye. That's why for any switchboard rated 800 amps or more, the standard says you absolutely must have protection to automatically shut it down and limit the damage.
To make sure that protection is fast enough, the standard gives us this very formula. It's a way to calculate the absolute maximum time the device can take to clear the fault. The whole idea is to cut the power before the arc's energy release gets to a point of no return.
Okay, let's make that formula real. Say we have a pretty standard 800 amp main switchboard. We run the numbers, and we figure out that if there's an arcing fault, the main breaker has to shut everything down in less than 0.57 seconds, just over half a second. That's it. Any longer than that, and the energy released is so massive that it could cause a catastrophic failure of the entire switchboard. We've now protected our wires from melting and our switchboards from exploding, but the final, and without a doubt the most important layer of safety is all about protecting people. And that is the specific job of the residual current device, or RCD. Now, it's so important to get this right. An RCD's job is not to stop you from getting an electric shock. It can't do that. Its job is to make sure that shock doesn't kill you. It's constantly watching the current going out and the current coming back. If even a tiny bit goes missing, like 30 milliamps, it assumes that current is going somewhere it shouldn't, maybe through a person, and it cuts the power in about 30 milliseconds. Incredibly fast. But here's the catch. In our modern world, not all RCDs are created equal. Your standard, old-school Type A RCD is fine for simple circuits, but all our new electronics, washing machines, solar inverters, you name it, they can create weird DC leakage currents. And the scary part is, these can blind a standard RCD, so it just won't trip when you need it to. That's why we have these other types, A, F, and B, that are designed to see these more complex faults. Picking the wrong one isn't just a small error. It can make the RCD useless and give you a totally false sense of safety. And that really brings us to the final, most critical question you have to ask yourself. The basic safety rules from the standard are timeless, for sure, but the stuff we plug into our outlets is changing all the time. So the big takeaway here is this. Making sure you have the right type of protection, and especially the right type of RCD for modern loads, isn't just a good idea anymore. It is absolutely essential to ensure the entire system is truly safe.